the next topic of discussion in this chapter deals with impulse. It turns out that impulse is the same as momentum. It's just from a different viewpoint. We know that momentum is defined as m times v. We also know that force is m times a. So if we were to find the fact that a times t equals v, then if we will take that a times t and put it right here for v, then the momentum can be calculated by taking m times a times t, mass. Okay? But since mass times acceleration is force, then we can replace the F for ma, and we get force times time equals mass times velocity. That means then that we have the same value written two different ways. We know that this is considered to be momentum. This is now known as impulse. And it's going to be a matter of how long a force is applied over a certain period of time when you're going through either a momentum or a change in momentum, most likely, which we're talking about. The label for that, since it's force times time, use I for impulse, actually use the right letter this time. And the label for that is going to be Newton seconds, or N times S. Okay, so let's go to page 216 and take a look at number 19. In which case is given us in that problem an impulse of 3.0 Newton seconds, and the mass of the object in that problem is 0.2 kilograms, and we know that momentum is mass times velocity, so we solve for velocity by taking 3 divided by 0.2, and that'll be 15.0 meters per second. Yeah, it's that simple. This isn't bad at all. Let's continue with problem number 23 now. In this particular problem, we're dealing with a change in momentum. Now we have to understand that in this particular problem, number 23, we're describing a ball being bunted, balls being thrown at the batter at 15 meters per second, and it's being bunted in the opposite direction, and it's going to be 10 meters per second the other way. So the change in momentum, the mass of the ball hasn't changed, but the velocity has. So the change in momentum is always be involving a change in velocity. Well, the mass of the baseball is 16 kilograms, and the change in velocity, well, it's being thrown at you at 15 meters per second, then you bunt it, it's going in the opposite direction. The velocity, which has to have direction with this, will be negative and comes back to 10 meters per second. Okay? So when we do this, we get 4 kilogram meters per second. Now we know that impulse, which is F times t, equals momentum. Alright? So it says that the ball was on the bat for 0.025 seconds, so the force times 0.025 seconds equals the momentum, which is 4.00 kilogram meters per second. We divide by 0.025 seconds, and the force then becomes 160 newtons. Okay? Last one we're going to look at is number 31 on the next page. In this case, this is another baseball. Well, baseball is really kind of a good sport for doing scientific types of things. But in this particular case, again, we have the change of momentum equals the force times the time. So in this case, the weight of the ball is 0.42 kilograms. The ball is being pitched at a speed of 45 meters per second, and after you hit it, it's going at 60 meters per second. The opposite direction, hence the negative sign. This could have been negative, this could have been positive. You would have gotten a negative answer, but what the absolute value of the impulse. There's no positive or negative for the impulse unless you're describing a direction, which is possible. The time that it lays on the bat is 0.04 seconds. If you ever get a chance to see a slow motion of a person hitting the ball, it's kind of cool the way the ball kind of wraps around the bat, already swing, and then release. So this is a legit thing. And in fact, I'm surprised it's on there that short of a period of time. But regardless, you solve for F when you divide by 0.04, and your answer is a number I forgot to write down. So let me punch this out in the calculator. Oh, there it is right there. It's 368. So that's all there is to it. So your practice problems. In 1617, those 5 problems, just do part B, number 24. Have fun.